Welcome to True Projects. In this video, we are going to explain the project YOLO, a robust object detector in adverse weather. Introduction. The project addresses a critical aspect of computer vision, that is, object detection in challenging weather conditions such as rain and haze. The primary focus is on developing a robust object detection system with the goal of improving precision and speed, particularly in applications like autonomous driving and robotics. Object detection plays a vital role in various perception systems, but challenges arise under adverse weather conditions like haze and rain, causing image quality degradation. Current detectors trained on normal weather images often fail in adverse conditions, posing risks such as traffic accidents. So, the project aims to overcome this limitation, ensuring the reliability of object detection in diverse weather scenarios. Capitalizing on advancements in convolutional neural networks, that is CNNs, and large scale annotated datasets, the project introduces a novel methodology. Rather than relying on conventional image restoration techniques, the emphasis is on unsupervised domain adaptation, that is UDA. And the proposed framework, RYOLO, that is Robust YOLO, employs a two-step process involving an image quasi-translation network, that is QTNet, and a feature calibration network, that is FCNet, to systematically reduce domain gaps. And the project holds potential benefits for applications relying on vision sensors such as autonomous driving and robotics. By addressing challenges posed by adverse weather conditions, the robust object detection framework enhances safety and reliability in practical scenarios. Importantly, the proposed methodology, compatible with YOLO series detectors, ensures widespread adaptability within the computer vision community. Objective of the project. So, as I mentioned earlier, the main aim is to build a strong system for spotting objects, especially in tough weather. This helps improve accuracy and speed, especially in self driving cars and robotics. And the goal is to set up and use various YOLO models, namely YOLO V5, YOLO X, RYOLO V5, RYOLO V3, RYOLO X, and YOLO V3 within the collab environment. This involves configuring and running these models to achieve reliable and accurate object detection. And the integration of our YOLO models specifically focus on using unsupervised domain adaptation, a technique that helps the models adapt to adverse weather conditions, thereby improving object detection reliability in challenging scenarios. And the project aims to evaluate the effectiveness of the implemented models using key metrics such as precision, recall, and MAP, that is mean average precision. The assessment provides insights into how well the models perform. Subsequently, fine tuning based on these evaluations is conducted to optimize the models for better real world performance. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front end framework used is Flask, back end framework used is Jupyter Notebook, database used is SQLite 3, and front end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is importing required packages. In this step, we import essential packages such as NumPy, Pandas, sklearn, TensorFlow, Keras, and Matplotlib. These libraries lay the foundation for subsequent data exploration, image processing, and model development. The second step is exploring the dataset. So, the dataset exploration involves a detailed examination of city images with and without fog. The process includes reading and plotting these images, gaining insights into their characteristics. Understanding the dataset is crucial for informed pre processing and model training, providing a basis for addressing challenges posed by adverse weather conditions. The third step is image processing. So, image processing is a critical phase where raw images are transformed for model compatibility. This involves converting images into blob objects, defining classes and bounding boxes, and converting arrays to NumPy arrays. These pre processing steps are essential for creating a suitable input for the subsequent stages of the project. The next step is loading the pre-trained model. In this step, a pre-trained model is loaded for the computer vision task. The process includes reading the network layers and extracting the output layers. Leveraging pre-trained models accelerates the development process and ensures that the model is initialized with knowledge gained from extensive prior training on diverse datasets. The next step is image processing again. So following the model loading, additional image processing steps are performed. This includes appending image annotation files, converting color spaces, BGR to RGB, creating masks, and resizing images. These steps refine the dataset, preparing it for further analysis, training, and evaluation. The next step is data augmentation. So, data augmentation enhances the model's ability to generalize by introducing variations in the dataset. Randomizing images, rotating them, and applying transformations contribute to a more robust and adaptable model. Augmented data helps the model better handle diverse real world scenarios. The next step is installing the packages required for YOLO v5 in Collab. So, for seamless integration with the YOLO v5 model, the necessary packages are installed in the Collab environment. This ensures compatibility and provides the tools required for effective implementation and training of the YOLO v5 model. The next step is processing the data based on YOLO v5 model. So, here, data is prepared specifically for training the YOLO v5 model. This involves organizing and structuring the data to align with the model's requirements, facilitating effective learning and inference in object detection tasks. The next step is training and building the model. So, the project involves experimenting with various YOLO versions, including V5X, RYOLO V5, RYOLO V3, RYOLO X, and YOLO V3. And in the next step, as an extension to the project, exploration of other models like YOLO V5 by 6 and YOLO V8 is conducted to achieve a robust and accurate final prediction. This phase is crucial for model development and optimization. And for user testing and interaction, a front end is built using the Flask framework as an extension to the project again. And the inclusion of user authentication with SQLite ensures a secure and personalized experience. So, this integration enables users to input images, triggering the pre processing and detection pipeline with the trained model. After signing into the system, users provide input images, which undergo pre processing using the trained model. This phase involves preparing the input for the model's detection capabilities, ensuring that real world images are processed effectively. And the processed images are used for training the models. And the final outcome comprising object detections is displayed through the front-end interface. Users can visualize the model's predictions, providing a tangible and user-friendly output for practical applications and evaluations, which undergoes pre-processing. So this phase involves preparing the input for the model's detection capabilities, ensuring that real-world images are processed effectively. So the processed images are then fed into the trained models for detections. And the final outcome comprising object detections is displayed through the front-end interface, and users can visualize the model's predictions, providing a tangible and user-friendly output for practical applications and evaluations. Now we'll understand about the algorithms used. So the first algorithm built is YOLO V5, that is You Only Look Once version 5. So YOLO V5 is an object detection algorithm that employs a single neural network to simultaneously predict multiple bounding boxes and their class probabilities in an image. So YOLO V5 improves speed and accuracy over its predecessors. It divides the image into a grid and predicts bounding boxes based on features within each grid cell. YOLO V5 is chosen for its efficiency and real time performance, making it suitable for applications like autonomous driving and robotics. The next algorithm built is YOLO X. So, YOLO X is an evolution of the YOLO series designed to enhance accuracy and efficiency in object detection. It introduces a panoptic feature pyramid network, that is PFPN, and a positional encoding mechanism, improving performance across various tasks. YOLO X is selected for its advancements in feature representation and its ability to handle diverse scenarios, aligning with the project's goal of robust object detection in challenging weather conditions. The next one is YOLO V5. So YOLO, that is robust YOLO V5, focuses on improving object detection in adverse weather conditions. It introduces a novel methodology involving unsupervised domain adaptation, that is UDA. The framework includes an image quasi translation network, that is QTNet, and a feature calibration network, that is FCNet, to reduce domain gaps systematically. Our YOLO V5 is specifically tailored for challenging weather scenarios, enhancing the reliability of object detection in adverse conditions. The next algorithm built is our YOLO V3. Similar to our YOLO V5, our YOLO V3 aims to address challenges in adverse weather. It utilizes unsupervised domain adaptation and incorporates advancements in convolutional neural networks, that is CNNs. While it shares the goal of robust object detection in challenging conditions, our YOLO V3 differ in specific architectural and methodological aspects from our YOLO V5. The next one is our YOLO X. So our YOLO X combines the robust features of our YOLO with the advancements introduced in YOLO X. This hybrid approach leverages both the domain adaptation techniques and the improved feature representation of YOLO X to enhance object detection under adverse weather conditions. Our YOLO X represents a fusion of innovations from different YOLO variants to achieve superior performance. And the next one is YOLO V3. So YOLO V3 is an earlier version of the YOLO series and remains a popular choice for object detection tasks. It divides the input image into a grid and predicts bounding boxes with class probabilities. YOLO V3 may have slightly lower accuracy compared to newer versions, but is known for its simplicity and effectiveness. Its selection in the project is based on a balance between accuracy and computational efficiency. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. Precision measures the accuracy of positive predictions, representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis, I have recall scores and on y-axis I have algorithm names. So recall assesses the model's ability to capture relevant instances calculated as the ratio of true positives to true positives and false negatives. This is MAP scores comparison graph. In this graph on x-axis I have MAP scores, that is mean average precision scores, and on y-axis I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in these folders, I have the required dataset. This is the sample folder in which I have images on which we will make the detections. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. These are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python. space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password, and click on login button. So it has redirected us to the detection page. So now we have to upload an image and the application will detect the adverse weather. Click on choose file button. So from sample folder, I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So the application has detected the weather and it is normal. And we can also see the probability score, which tells us how confident the model is about the detection. And we can also see the bounding box drawn. Now click on back. We'll try giving another image. Click on choose file button. This time I'm giving this image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected the adverse weather. It has drawn the bounding box and we can see the detection, that is foggy. And we can also see the probability score. Click on back. Click on choose file button. This time I'm giving this image and click on open. The image is loaded. Now click on upload button. So we can see the detection, that is normal. Similarly, we can upload any image and can get the detections. Click on back. Click on choose file button. This time I'm giving this image and click on open. So the image is loaded. Now click on upload button. So we can see the detection is normal again. Now click on back. Click on sign out button. So the conclusion here is the project successfully achieved robust object detection, specifically addressing challenges presented by adverse weather conditions, enhancing safety and reliability in practical scenarios. The project implemented a range of YOLO-based algorithms including YOLO V5, YOLO X, RYOLO V5, RYOLO V3, RYOLO X, and YOLO V3. Each algorithm contributed to the project's goal of accurate object detection under varying conditions. In addition to the core algorithms, the project explored extension models such as V5/6 and V8. These extensions aim to improve the robustness and accuracy of the final predictions, contributing to a more comprehensive and adaptable object detection system. And the project integrated a front end using the Flask framework, allowing for user-friendly interactions. The Flask integration facilitated user testing, where input images could be processed by the trained model and the final outcomes were displayed through the front-end interface. And the beneficiaries of the project include applications reliant on vision sensors such as autonomous driving and robotics. By addressing challenges posed by adverse weather conditions, the robust object detection framework enhances safety and reliability, benefiting users in real-world scenarios.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.